Morning. You asked for homework solution to be posted, and so I wasn't planning to answer the first question. Is that all right with you? I mean, I don't think you need to read a narrative. But the second and third ones are the ones that I think you need. Is that correct? Okay. And rather than like the fourth one, I don't really care about either. That's mainly for your information, and the fifth one is sort of nonsense. So I have, the issue is that I have a spreadsheet. So what I want to do is put the spreadsheet on Canvas for you. And then the problem with spreadsheets, perhaps I should ask that as a question. What's the problem with spreadsheets in general? Well, they're great tools, right? There's no question about that. The issue is you have to think like the person who created the spreadsheet. That should give you pause. So the first one here is this is question 2. Down at the bottom, let's say Q2, Q3, etc. And so I told you that you could pick materials out of the spreadsheet that's online, right? That's on Canvas. But I don't care. I just took the one right out of the homework set at the bottom. This is what is at the homework set at the bottom. Okay, I just took that as is. And then selected my raw materials. So 4, 3, 2, 1, right? 40, 20, 30, 10. And then I identified what those were going to be so that it would be easier to deal with. G200, Huber-Carb, Flint, and EPK. And then these are their chemistries from above, but ordered in the right way. And then contributes from each raw material. And then what should happen is that in the cell, you have the equation. You should be able to follow that. And I don't know if you're familiar with how familiar you are with Excel. I find that varies widely in terms of your ability to use Excel. If you double click on this, it should tell you then the cells that are used to calculate, unless you have it set up to edit directly in cell, which I cannot come up with any reason why anyone would wish to do so. Yet it's an option in Excel. If you turn that off, double click will tell you what cells were used to calculate. Good? So then that's the way that you can navigate backwards through the spreadsheet to see how I did it. And then sum of the oxides on a mass percentage basis, there's the molecular weight, there's the moles, and then the sum of the fluxes is over here. And again, if you double click, you'll see that that's the way it works. Then you get the UMF and then your silica to lunar ratio. And I did not plot it on stall. Do you need me to plot it on stall for you? Can you plot on an XY axis? Oh, good. So you don't need me to plot on stall. Okay. Question 3 is more complicated because question 3 says, for one of the compositions listed at the phase diagram attached, calculate the following. UMF of the body composition. So basically what I did was much the very same thing, except I went through over here on this side and calculated for metakaolin, etc., based on LOI values. Okay, and there is a summation of that. Okay, and then correcting for LOI and free quartz. And the reason that it corrects for free quartz is because you get free quartz out of the ball clay. You get almost no free quartz out of the EPK. Someone had a question last week about EPK. Is it you? Can you repeat your question?
I asked why the LOI was higher than
Yes.
calculated LOI.
Was it in the spreadsheet that you found it that way? Or was it in the handout?
On the homework it gave the LOI and then I just used the
Ah.
But I think on the homework too it had the value.
Right. Here? Homework 2 or homework 3?
Homework.
Oh, 2. LOI. So, all right, there's a number of things that are going on that sort of has a historical context. All right, first things first. I I started teaching this in this way about 22 years ago. And at that time, I was teaching artists about how to do the calculations for UMF. And so I took raw materials that I had, and I did all the PowerPoint presentations based on those raw materials that were at hand at the time. And then a few years later, I went back and compiled a considerable mountain of chemical analysis data that we had collected over several years. And I revised the spreadsheets to have all the raw material chemistries, and those are the ones that are posted on Canvas. That's the one primarily. Then there was a problem. The problem was that the chemistry that I used to do the to do the PowerPoint presentations for artists for doing the calculations for glazes didn't match now the LOI in the spreadsheet because of compiled the data, made the numbers a little bit different. And so because I was basically lazy, I didn't go back and correct all the PowerPoint presentations because that was a lot of work and it just wasn't necessary, except it creates a problem. So then what happens is in the spreadsheets there might be 2 entries for EPK so that I would still have the one that was in the PowerPoint. Does that make sense? So basically, you can accuse me of being lazy and I will not do that. But the consequence of that is that you will see that the chemical analysis from several of the raw materials don't always match in all of the different versions that you get. So the question is, do you care? No, not really. If you look at this EPK chemistry versus the one that was in the first spreadsheet like this one, they're pretty close. Now you can argue whether they're really pretty close or not, but they're identical in this case, and then in some others they vary a little bit. But the issue here is that the LOI is greater than 14%, and we predict that 14% is for a pure kaolinite. Why is the LOI? Give me 2 reasons why the LOI could be greater than 14% for EPK. Or for any clay. So LOI is a rule of mixtures for different mineral phases, right? And then you have also other things that show up like organics. So if you have a clay with a lot of organic, right, then 100% of that organic goes to LOI. Right? So then a small amount of organic could kick your LOI up, provided there is no free quartz. You got a lot of room there, okay, before you run out of, what I'm saying is that since it's 100% loss versus 0% loss, you have a lot of room. A small amount of organic can make a difference. We have not found that to be significant in most of the clays that we look at. There's only a few that have significant organic matter. The ball clays are typically higher in organic matter than the kaolins for a couple of reasons. Most of the kaolins are wet processed. That means they're slurried in process. Organic matter then typically is hydrophobic and will float to the surface. If you make a suspension of clays, you will also often see that on the surface of that suspension will be little black specks, and they are organic matter that comes out of the clay. But it's a really small amount. The second is that EPK contains smectites, and it contains a significant amount of smectites. And so with EPK, we have smectites, or montmorillonites, if you will. Strictly speaking, they are not bentonites because bentonites are volcanic in origin, and in Florida we don't have much volcanic activity. Okay, so what you get out of that is smectites because they are essentially 2-to-1 sheet silicates, right? But then they have this oriented water layer, and sometimes exchangeable cations, and that's variable. So as you may recall, right? This distance here is about 15 angstroms. And it has to do with this water layer, and that kicks up the LOI if you have a significant smectite level. And EPK is known for that. So what happens is that if you look at EPK, and frankly, if we, even more importantly, look at the chemical analysis of EPK, hang on a second. We find, and we look at the UMF for these clays. Right. and you go to the spreadsheet. If you go to the spreadsheet that's done everything that is done based on UMF, okay? So if you look at the bottom here, along the bottom it says UMF, this tag here, okay? So you have weight percentages, moles, molecular weight, and so they talk into the molecular weight in the UMF table, and then UMF. What's great about that and is really good for us in terms of understanding these materials better, when you look at all the clays, okay, now zip this down to where we get to EPK. In this spreadsheet I've compiled it so you don't have two versions anymore. This number here, the 2.37 number, for example, tells you then the ratio of silica to alumina. Does that make sense? Okay, and what do you expect that value to be? If it's a pure clay, a pure kaolinite, you'd expect that value to be 2. Okay, so EPK is pretty close to being 2 to 1, silica to alumina. ESVA is actually a little too good. ESVA is it's an English China clay. If I looked at Grollig, which is in here, 2.12. If I look at SSP, supercenter porcelain, those are, let's see if we have it here. Supercenter porcelain, 3.01, that's a little bit high. If I look at OMI number 4, that looks remarkably good. That's ridiculous. So usually it's an indication of the amount of free quartz in the clay is based on this number. Okay, so EPK is pretty close. And you can see in this vicinity that there's a bunch of these that have a lot of extra silica in the clay. So EPK is there with 2.37, and then the extra LOI is because of montmillinite to the EPK. So what do we do with that? We ignore it. Okay? So that sort of answers one of your other questions. On the spreadsheet here, I convert first to correct for the LOI and the clays, and then also to correct for the free quartz that comes out of the ball clay. So this is for plotting. So I have metakaolin, right, feldspar, and quartz, and then these are the values that get plotted, and they are from this composition list. Does that make sense? So to plot, because you can't plot on the phase diagram clay directly because there's no water on the phase diagram, you have to correct that then for the metakaolin. So that's done here. And then the LOI, not the LOI, the UMF values don't care about that LOI because they are based on the amount of silicon, alumina, etc., and the water is unimportant, and that automatically comes out of that calculation because in the end, it's simply gone, right? And you don't have to compensate for it, and because it is incorporated into the chemistries already. In other words, we do a chemical analysis, you get the amount of silicon, alumina, sodium, potassium, calcium, magnesium, whatever. But we don't pay attention to the water anymore because that's actually what comes back from the chemical analysis, which is why it does not equal 100%. And then when we get all done with that, you can calculate then the UMF of the body, which is here, okay, moles, and then UMF. What we found in most body compositions, we're about 4 moles of alumina. On a UMF basis, alumina is always around 4 to about 5, and silica is about typically 17, about 25. Depends on a bunch of things. I don't know what these work out to be exactly. Let's see. There's 19 and a half, and there's 20. Okay, and we're 3.5 there, etc. So I could reduce that a little bit. And then the sum of the fluxes is always equal to 1. So that's the UMF. Good? Okay. So it's done for all 3 compositions. The moles here, this is going to a, yeah. There's a list of the molecular weights in the spreadsheet, and you use those. You don't have to use those, and if you don't use those, it alters your numbers a little bit, but you should be pretty close. Once you have the UMF, then that takes you to question, this is A, B, and C. in the homework. A, B, and C in the homework. And it also requires you to plot, right, locate the composition. And percent molite possible is based on the alumina level in total, not based on the amount of glass in the system. And then the question 3D, calculate the range of molite possible, is done for you for each of these, okay, based on the molite levels that you would expect for the three materials. And then this should help you walk through that problem. Good? So numbers are done, and you can deal with it that way. The rest of the questions I don't really care about. Economics of porcelain, ancient history. Good? Okay? Questions about that? Let's talk about the exam briefly. I've been pinged by several of you in terms of when the exam is. And I think that you have misinterpreted my level of interest or overestimated my level of interest. I don't care when the exam is. So you just got to tell me when you want it, and I will do that. What's that? Next Wednesday. I still don't care. So here's the thing. This is how it's going to be. All right. There's going to be two parts to the exam. There'll be an in-class portion. We'll do it this way. Christian is out, I think, until Friday or something like that. Okay, so that makes it a little tricky. Alicia, I've asked Alicia to proctor the exam. Okay, and the way I'm going to do it, I'm going to have it set up. There'll be an in-class portion, okay, which is a bunch of multiple guess questions and things that you should know. Okay, I don't care when you take that, but it's not appropriate for Alicia to be at your beck and call. Fair enough? Okay? So what we need to do is set a time. I'll make it a couple times. I don't really care about that. And then there'll be a take-home portion that I assume you'll all get together and do at one time. Even though it says groups of 2 to 3. Okay? Because that's what always happens, and I'm not naive. I know you're going to say, how do you do this problem? And a little like the blind leading the blind at that point, I think. So anyway, all right, so it'll be a two-part. I don't care when you do the second part either. The return date will be Monday, the 7th of October. Good? And it will be a problem. It will be sets of problems that have to do with, let's see, do I have an example here? Oops. Usually I try to work out the exam questions before I give them because they don't always work. It's a little bit aggravating when they don't work. There's midterm 1. So you can see, yeah, that's pretty much it. Calculations regarding materials, etc. Something to plot. Won't be any multiple guess on it. So that'll be more or less what you see. I mean, I don't care if you have this. It's going to change somehow. Okay. Fair enough? So what I'm going to do is set 2 dates for you to take the exam. You're going to MS&T. Who else is? Anyone else in here going to MS&T in Portland? Yes? No? So you're it. Next Wednesday is when you want this to happen? When do you get back?
Saturday. Next Saturday.
Saturday? All right.
Can I do it Friday?
Yeah. Do you want to do it in Portland?
No, this Friday.
This Friday? You mean early rather than later? Sure, I don't care. Anybody else would take it Friday also. I don't know what time Christian leaves, but we'll make it. I'll give you those times after I talk with Alicia and Krishna. I'll give you times. It'll be 2 times when the exam can be taken. Then how's that sound? Wednesday in here will be one of those. The other will be Friday at some time. Good? Okay, good. Any questions? this is where we are at the moment in terms of homework. And this is the, we're getting into colloidal behavior. Yes?
You have classes Wednesday then?
Yes, you do. Okay? So there's still an opportunity for discussion on Wednesday, of course. Okay? But you do not have class next week. You can show up, but I won't be here. So. All right. So, where we are right now is that we're done with structure. Okay, we're done with raw materials more or less, and we're at the point of moving into colloidal behavior. And so, let's see. There's one other thing that I wanted to bring up that I forgot about, so let me do that real quick. I forget about it because I don't care for it as a test, but it's used a lot. And clay characterization. And it's called the methylene blue index. And so where we are in rheology and dispersion, though, that's where we are now. And there will be some parts of this that will show up on the exam. Okay. I'm not going to get into ionic strength effects and all that kind of stuff at this point. All right. So let's see. I mentioned this briefly before. Now I don't have a slide for it anymore because I don't believe in it. So there's a test called a methylene blue index or a cation exchange capacity, a CEC. And you will see that that listed on clay data sheets. Cation exchange capacity. And it has to do with I'm not going to be able to find it. It has to do with an idea that for clays that had exchangeable cations, what does that mean? What is an exchangeable cation? Sports fans? You just did the classic move. Look at me and put your head down because I've seen that before. What is an exchangeable cation? See if I have the slide I need. I do not. Okay, when we get into montmorillonites in particular, there are ions that are argued to exchange for one cation on the surface versus another. Okay, and this is probably as good a thing as any. Let's see. Okay. So what you get is that ions in solution, and there's a thing called a Hofmeister series, which we do not deal with typically. And it says that calcium, for example, will replace sodium on the surface of the clay. All right? And so there's a whole list of these, and it goes something like this. Ammonia, sodium, potassium, and then it does magnesium, I think, and then calcium. And this is a replacement series, so that one ion can replace another on the surface. So the idea would be that the affinity of, say, calcium would be greater than sodium on the surface of the clay, and therefore what it would do is the calcium will go in and displace the sodium, so it kicks the sodium back out into the solution. Okay, so it's called a cation exchange, so you're exchanging one cation for another. The problem is that this is not quite correct in that there is a sequence, but if I elevate sodium ion concentration in the bulk solution, now sodium can replace calcium. So it gets a little confusing. There's what's called a complex ionic equilibrium set up on the surface of clay particles. And all of that is put together. Most of these cations are coming from this interlayer spacing, if you will. Okay? So in smectites, most of them come from smectites. There's no place in kaolinite for an exchangeable ion. Okay? There's no way that you can fit it into the lattice. It's just not possible. All right? So when we do a CEC, we do what's called a methylene blue index, MBI, and you will see this if you look at clay data sheets. Okay, so methylene blue is an organic molecule which is supposed to be cationic. Okay, that means that it is a charged molecule, positively charged molecule, and it will specifically absorb on the surface of a clay particle, ideally displacing an ion that's already there. And then you can look at how much methylene blue is taken up by the clay, and by measuring that amount, you get a methylene blue index, and then that's supposed to, your MBI equates to a cation exchange capacity. So it's a test that was done to evaluate clays. Now, there's another thing here that is supposed to correlate, which I'm not convinced does, and that is that this gives you an indication of plasticity. And I'm going to put a big question mark on that because I don't think that's true. Okay, so then what would happen is that if you had a certain cation exchange capacity or methylene blue index, then you would get a certain plasticity out of that clay. So it's actually set up to measure that plasticity ideally for that material, right? And then that index comes up, and you can measure that on a clay, and it's listed in terms of milliequivalents per 100 grams. And so MEQ per 100 grams, and a milliequivalent then is a charge, right? An equivalent is a charge if you go back to chemistry. So if you had, say, sodium, that's 1, calcium is 2, etc. Okay? So you get this milliequivalents per 100 grams. What's the problem with this? Is that this ignores specific surface area. Because it's telling me that I have 100 grams of clay, I can come back with my milliequivalents. Well, what happens if my clay is, say, 25 meters squared per gram, or compared to 15 meters squared per gram, right? So if I'm a lower surface area or a higher surface area, I would assume that my cation exchange capacity would go up with an increase in surface area. Make sense? Okay? This does not correct for surface area. Now, there was a guy named Ma, M.A., who's probably another author, co-author, wrote a really nice paper about 15 years ago demonstrating that the methylene blue index for kaolinites was solely based on the amount of impurity minerals in the system, that there is no cation exchange capacity for kaolinite by itself. Really nice paper. Are essentially saying that the methylene blue index was a waste of time, which is what I believe. Okay? But it is measured. So what you have in a commercial clay is they will list an MBI or a cation exchange capacity, and then what they will do is they will blend clays to maintain that cation exchange capacity. So that means if you are low, so if I go to montmorillonites for smectites, that this might be 100 milliequivalents per 100 grams, right? Where if I go to kaolinite, it might be closer to, say, 20, okay? But it's not 20. It's if I measure a kaolin, I get a low value. If I measure, or a ball clay, I get a low value. If I measure a clay that contains a lot of smectites, I get a high value. And there are montmorillonites available that are relatively clean, and you measure these values, you get very high cation exchange capacity. So what what they do in the mine is they mine clays from different regions in the mine and they stockpile them, right? So they'll have, location A, they have a stockpile there, and then location B and location C. And so basically what they do is that they they then blend from those different stockpiles to give a specific methylene blue index. So what they are trying to do is maintain that methylene blue index value to be uniform, but they will blend then clays to maintain that methylene blue index. My argument is that that's a problem. And the problem is that you end up with, occurred to me is one other thing I got to do. You end up with different surface areas in those clays then. You see what I mean? So you might be blending these clays to maintain that methylene blue index, but your surface area is changing. And then the dispersant demand will change and the behavior of those clays may change. And then you're actually chasing potentially the wrong thing. But you will see this. This is called an indicator method. Do you know what that means? What is an indicator method? What's an indicator? We've all had chemistry or you wouldn't be here. Something that changes color. Methylene blue is blue. Okay, and as you, what you do is you put it in, and then you remove the clay, and you have what's left in solution, and then you measure how much is left in solution by bringing in I think it's an acid, and it's probably a base, and then you neutralize that, and by the amount of acid that you, or the amount of base that you use, tells you the amount of methylene blue in solution, and the amount that's missing is the amount absorbed on the clay. So basically, you look for a color change as you titrate. And then from that titration, you figure out how much methylene blue is there. Okay, so that's the methylene blue index test, basically. It occurs to me there's one other thing that has to do with how these clays are mined, and we're going to do that right now. So there we go. In 2000, we organized a symposium in St. Louis at the American Ceramic Society and invited all these people to come and talk about really odd. This guy, Jason McCutcheon or something like that, he worked for H.C. Spinks, gave a spectacular talk on quality control for ball clays. So Spinks, there's only a number of companies in general. There's Spinks and Old Hickory and a couple of others in Kentucky and Tennessee. They're the bigger ones. And then in the Georgia Kaling group. Okay, you've got a whole bunch of little companies now. Anyway, he put together a really nice talk about how this works. This is his process flow chart for mining clay. Okay. Oh, by the way, the reason I don't like this test, right, there's two reasons. One is there is some operator contribution to the test, and the two people doing the same test, they weren't trained the same way and may get a different result. We've run across that in the past. We don't do the test because I don't believe in it, although I probably should so that we can document why we don't believe in it. And then the second part is that I don't believe that the cation exchange capacity actually relates to plasticity. Okay, there's a third one too, which is that you're not correcting for surface area. So if you do it for surface area, we're in much better shape. So this guy, Jason, gave this great talk and gave me the slides afterwards. Basically, this is a process flow chart, and it looks at how you exploit or mine a clay deposit. And at the top, start off with drilling holes on 150-foot centers, typically in more or less a hexagonal array or a square array. And you're doing boreholes, okay? And then when the borehole, when the core comes out, you sample the core every 2 to 3 feet, okay? Sometimes you can look at the core and you can say, oh, overburden, shale, clay, etc. And some of those cross sections of hills I showed you, I'll show you one in a minute. You can see that. And then does the deposit look good? And if it doesn't look good, then you go someplace else. And so recognize that in the ground, the clay actually has something that looks like this, right? It's sort of a lens-shaped thing. And so as you're drilling boreholes through this, right? You get to a point where, oh, no clay, okay? And they may not be oriented horizontally, they may be at an angle, you know, and it has to do with the deposition conditions when that clay was stuck in the ground. It looks good. They surveyed the property. They produced a 3D model, and if there's problems there, and that 3D model tells them if it's going to be economical to mine clay, because a thin section of clay isn't worth going after, and how deep does it have to be, and what's your overburden, what's your access to the deposit, etc. All this is done by strip mining. Nobody mines clay underground except the Chinese 1,000 years ago. Okay, so they have a mine strategy. They strip the overburden. They production drill on 75-foot center, so they go in and take more core samples. And what that does is it creates this whole map of exactly where the clay is. And it used to be different. Now you understand that on the front end of on the bucket of a front end loader are GPS sensors, and it tells them exactly where to dig. And then that material comes back out, gets processed, and all that information is logged. And this was being done 20 years ago with GPS. So here's exploratory mining. The bottom is not very visible. The dates that are in there says 97-17, 9710, etc. There are date pieces of information in there, locations, okay, and then they create this map, which is awesome, okay, and this is all this area here. I don't know what the thing in green is. This is sort of their. This is a part of this map that identifies where the location is. All of this material was measured or core drilled, and then this material is core drilled. And this colored area up here, okay, if you look at it more closely, this is that region, and then these are the voids that were opened up. These are actually the mining in sequence. And so what you can see maybe is it says void number 1, September of '98, void number 2, November of '98, and then here's void 3, March and April of '99. Void 4 is in June of '99. Void 5 is in September and October '99. Here's 6 in November, and 7 is in 3. If you pay attention to the dates, there are gaps. So it isn't they don't mine all year round. They don't mine all year round because apparently, if I look at this, it must rain in May. Okay? If it rains in May, you're not in mine. Like I said, it's a huge multi-acre slip and slide. And then remaining uncovered clay. So they're mining this in a sequence and then they're working their way down into clay. And they're not going to mine out here because there's nothing of interest and you can see where the deposit goes. Okay? And then they construct this three-dimensional model. And then they produce that model and they look at what it's going to look like essentially. And then they say, well, I don't know, let's just say the blue is what we're interested in. Okay? And then what's in the yellow, I don't know. Okay? And it may be that this lighter blue at the bottom is also of interest. Okay, so you have something in the middle that's not of interest, and there's a really interesting picture coming up. And then they estimate the tonnage, they predict the planning or the timing, how long it's going to take or how long it will last. And then they develop long-term plans about how they will exploit that deposit. So there's a lot of things going on here, right? Where is the clay? What's the market look like? How expensive is it to get out of the ground? How good is the clay, etc. Okay, so they end up with this sort of a map, and these maps at the bottom are interesting because this is the depth of the deposit, essentially in a two-dimensional topographical map, and if the depth of the deposit is not sufficiently large, you're not going to mine it. So the red spots are the hot spots, if you will, and it says that the deposit depth is 14 to 16 feet, and where it's black, there's none. And then it goes on, and so you can see that this is the area of interest. Is going to be this green, 8 to 10 feet down to 14 to 16 feet, and that's the depth of that deposit. So then they do the cross sections, and they show here, okay, what the types of clays are, and then this is the picture that I was referring to. They're a three-dimensional map, and then a comparison to a cut. So it's a pretty interesting approach, and what I like about this guy, he's a clay mineralogist or a geologist, and And he had been working there for, I don't know, not very long, maybe less than 10 years. And he put all this together in terms of how the clay is mined. To the best of my knowledge, never had a presentation in that way before. That they walk through all the steps of how they do the mining. So, but this is their actual cross section, and this is the model that predicted this cross section. And you see, it's pretty good. Okay. So, and then there's the clay itself and how they mine it. Okay. So, and then it's stockpiled and it's blended on the floor. So they stockpile clay from different locations. They may have multiple mine sites, and each of those mine sites, the properties of that clay are different. Okay, and they put all of that together, and then they have a more or less a data sheet on all of the clay that comes into a warehouse, basically, or a shed, and then they know that we're going to blend. If we're going to make, say, what's called O mine number 4. We might have 5 piles that we go from. 2 scoops from here, 3 from here, 1 from here, and a half from here, whatever, and then that all comes together to make O mine number 4. And the idea is that you are trying to blend to maintain the consistency of O mine number 4. And so they also do that with feldspars, or should. They don't do it with quartz because it comes out of the ground about as clean as you're going to see it. Okay, they don't do it with calcium carbonate because it's not necessary. And so the consequence is that things that have variability, like feldspar, clay, etc., okay, they are blended to maintain that uniformity. And if they're good at it, and they're often very good at it, then what you get is really good uniformity in that clay. They blend on the floor, and what the blending of the clay does is it dampens the variations. Okay, and they will adjust then the scoops from each stockpile based on that variation. But what they produce then is a very uniform product. And so the Feldspar Corporation mined feldspars in North Carolina for years. And before that, they were called the Feldspar Corporation. Then they became CEMX, which was, and CEMX owned also EPK down in Florida. So the Feldspar Corporation, they were bought by this group. This is a group out of Mexico. And then it was bought by Imerys. That's spelled right. And Imerys is huge. And what they had in the feldspar mines in North Carolina is they had a very high quality potassium feldspar. And it was quite valuable and also extremely well known within the industry and highly respected as an exceptionally good raw material. And that was G200. And G200 was, by all accounts, one of the best feldspars around. And this was a potassium feldspar. In my opinion, now Imerys may argue that's not the case, but they were blending to maintain a ratio of approximately 70% K-spar and 30% soda spar. Okay, now we can argue with that just a little bit and say slightly different than that. There's a little bit of calcium in that system. Okay, about less than 10% in that typically. And this was on a molar ratio basis, not on a weight basis. So I had 70% potassium feldspar on a molar basis, and I had 30% sodium feldspar on a molar basis. And overall, based on the chemistry, I have roughly 10% free quartz, okay, which we hardly ever talk about. And that comes out of the fact that the feldspar deposits are feldspar and quartz. You remember the other impurities in a feldspar deposit? So I have feldspar, that's good. And my impurities then are quartz. What else? Do you remember what the feldspar mines were before they were feldspar mines? They weren't just rocks, by the way. A big field full of rocks. Right. Well, no, not exactly. So if you recall, mica was a big one, right? We talked about huge mica sheets for our windows. Isinglass. It's right across this. Mica. It was called isinglass. Used in furnaces, fireplaces, stuff like that. That's mica, actually. Mica, garnet, and iron. Typically, those were the impurities in the feldspar. So these are all removed. So G200 was a blend of a potassium feldspar and a soda feldspar. In the late 90s, they opened up a new deposit, and really spectacular, high quality potassium feldspar. Okay, but what that allows you then is years on the deposit, because you can then blend that feldspar with soda feldspar like NC4, which is a really famous soda spar, which comes out of North Carolina, hence the name. Okay, and then, but you would blend the soda and potassium spar to keep that ratio of chemistry the same. Imerys decided not to do that, and they came up with G200 HP, which I object to in several levels, but this is supposed to be high potassium, so they stopped blending that feldspar. Okay, and then what happens? You run out of feldspar. So G200 is no longer being produced, and that created all sorts of problems. Going to HP created problems. Okay, what problem did it create? Potassium is a higher molecular weight than sodium. So pound for pound, right? If you have a sodium feldspar and a potassium feldspar, you have more flux in the sodium feldspar on a weight basis, because the molecular weight of sodium is 62, molecular weight of potassium oxide is 94. So you're roughly, you're down by roughly 50%, okay, if you will. And so you want to look at it 1/3, 2/3. But the fact is that when you brought in an all potassium feldspar, high potassium feldspar, now what happens is you don't have as much flux in that body. Then you have to alter the composition of that body to compensate for the fact that you're not making as much glass in the body anymore. And the direct consequence of that would be underfiring. In other words, under the same firing conditions, you don't make enough glass, the body doesn't densify the way that it should. And that difference, although it seems like it would be subtle, that difference showed up in manufacturing. And they had to modify their compositions because they didn't have enough flux within a high potassium feldspar. And then they ran out. Now we have a big problem. There's only one other source for potassium feldspar in the country, and that is Custer. Custer feldspar. Where is that located? This is not a trick question. Where do you think a mine called Custer would be located? What's that?
Custer.
Yeah, where is Custer? Yes, exactly. Why?
That's where Custer got.
That's where he pretty much bought the farm, as it were, right? So Custer is from South Dakota. Okay. The problem is that Custer is a small family-owned business. They've been around for a long time, but they simply do not have the capacity to handle the demands of the industry in the United States. So there is some Custer that was in for some dinnerware production, and a lot of artists use Custer, and that market is good for them, and they keep that market. But when you go and you get somebody like Lap Insulator and Victor Insulator and Kohler, right, American Standard, and they all want potassium feldspar for making huge volumes of material, not to mention dinnerware production. They cannot handle the demand. And then the cost associated with scaling up to handle that demand is too high. So now we have a crisis, and we have a feldspar crisis in the United States. And now feldspars are imported from India. Okay? So, not happy with Imerys, but that's the way it works. But blending is important because blending gives you uniformity in the raw materials coming into the plant. Now, G200, we have some G200 HP left, and Art Design has a few bags of it left, and they're trying to figure out how to deal with it because it creates problems for them also. So that brings us to colloids, okay? And this is where we are. Of course we're here, and then of course you know that we are going to be here, right? And if you've had me in class before, I think all of you have pretty much. You need to know the 5 factors that control suspension rheology. Fair enough? You have to, the reason that you have to is because it's going to be on the exam. Okay, it's not going to be on the open notes portion of the exam. All right. So, why do we do this? Why did I do this? Rheology of suspensions is interactive between different things in that suspension. So, solids concentration is a big one. You'd like everything to be on the same solids loading. That way you can compare things that way. Particle size and distribution play a role. At the same solids loading, if I change the degree of dispersion, I can change the rheology dramatically between those different suspensions by adding dispersion or changing pH. So the problem that I have with all of this is that these things are all interactive, and in order to decipher what was going on with specific components, I needed to keep as much as possible everything else the same. Okay, so the last one here, rheology, the suspension medium, was because years ago I didn't care about rheology of the suspension medium, and we don't particularly care about it in here because everything is water, aqueous based, right? But I got invited to talk at an injection molding conference. It turns out rheology of the suspension medium is really important to them. Okay, so that got added. Particle interactions are the big one. They are critical for clays in particular. And as I increase the solids concentration, my viscosity goes up. The water content is probably the most abused. We talked about this a little bit last week, right? Orientation, thixotropy, etc. Right? And then particle size and distribution. Broader particle size means a reduction in viscosity. Particle morphology, spherical particles tend to have a lower viscosity than shaped particles. Plus, as the particles become spherical, your thixotropy goes away. And then rheology, the suspension medium. So we did this, and then we get to here. We talked about this, right? And that brings us to, I want to go to somewhere. Come on, there. Okay, so we have a small problem. We like to represent everything based on surface area. In that way, we can look at, if I have a particle, right, I know the surface area, then the polymer fits on the surface area, and it's a function of surface area. And I do my dispersant level in milligrams per square meter, so I'm correcting the amount of dispersant I bring in based on the surface area of the material. So if I do alumina, okay, what I find is that the optimum in terms of dispersion for alumina, milligrams per meter squared, and this is log viscosity. What I will find is that my curve is something like this, comes down like that roughly, and it will start increasing as I go past my optimum because of an increase in ionic strength, and that increase will be dictated by the amount of surface area in the system. So if I have a higher surface area, then I'm going to have to put in more polymer, but all of my polymer, all my PMAAs and PAAs and sodium silicates are bringing in sodium, and so that dissociates. Then that sodium starts to compress the double layer. So if this is alumina, the other thing I know is that my pH is about 8.5. And then this value is about 0.35 milligrams per meter squared is my optimum. Okay? So, to deal with that, you have to know how the polymer behaves. pH, and then degree of dissociation alpha, all right? And here is 1.0, and this is 0.0, and my curve looks something like this. Okay? And up here, at around a pH of 8.5, I have 95% dissociated. And so at that point, I have this reaction. This carboxylic acid group is associated with sodium. Okay? And so what happens is I drive up pH, that sodium will dissociate, and I end up with a negatively charged polymer backbone. N here is about 150 typically. This is polyacrylic acid. We don't care about N. N, though, tells me how long that chain is. Okay? And so when I put this in water, if I drive the pH up, I will dissociate that sodium. And if I drive the pH down, I will reassociate that sodium. And thus, I will end up eliminating this charge, cycles away. And that changes the conformation of that polymer. So if I'm down here around 3.8, I have about 5% dissociated, and my polymer will form a little ball with a few negative charges to keep that ball more or less dissolved. Okay? So if I reassociate this charged site, this polymer becomes hydrophobic. It doesn't care for water anymore, and it will basically ball up to minimize its exposure to water. Then you only have the exterior few charged sites on the surface. At high pH, when I start charging all of these things, then what I get is this sheet, not sheet, but long polymer chain with a lot of charged sites. And because, one, this material now likes water, because that carboxylic acid group is hydrophilic, and then the other thing that happens is I have charged sites adjacent to each other, and they will stretch out as far as they can to get away from each other. Okay? And so what happens then is that I end up with this essentially ribbon, if you will, of charge. So when I look at the amount of material necessary to coat the surface of the particle, it scales with that degree of dissociation. And so what I get is I get what's called a strong absorption behavior. So this is 1-to-1, and this is added, say PAA, and this is adsorbed. And what I get is I get behavior like this that comes up. And everything that's added is absorbed, everything that's added is absorbed, everything that's added is absorbed. And then when I get past that point, anything that's added that's not absorbed, it stays in free solution. This is called strong absorption behavior. And so the strong absorption behavior that I see with PAA indicates that these materials, that this polymer really likes the surface of that particle. So if I look here, where's my minimum in the dispersion curve for in this case, well, PAA or PMA, they behave the same, sodium silicate. So I tell you that alumina is 0.35, but if I look here, I'm closer to about half of that. Why? Is this an error in measurement, perhaps? Of course not. Why not? What's the problem? So I'm absorbing polymer on what surface in my suspension? So, what are the particles in suspension on the image projected on the board? What particles are in suspension? I just obscured the image for you. What particles are in suspension? No? It's a porcelain suspension, right? What's in suspension?
Alumina.
No alumina. Where's the alumina? Clay? Let's see, I'm looking for another presentation. Hang on. This one. Let's try this one. Okay, you have alumina. You don't have alumina. You have clay, quartz, feldspar, etc. Right? Good. We use this to illustrate morphology. Here's what I have. In suspension, I have clay, feldspar, and quartz. So you need to know something else. If I put particles in water, dependent on the particle, I will now get something like this. pH and zeta potential. So a particle in suspension will develop a charge, we'll make it positive for sake of argument, and I get a double layer around that particle. And I'm interested at the charge at the shear plane. Turns out that each of these materials has a series of reactions that occur that dictate what that charge is on the particle surface. So I have two pertinent curves here. Okay? I get the alumina curve, and I get silica. Alumina, isoelectric point around 8.5, the point at which the zeta potential changes sign. And for silica, an isoelectric point about 2.0. So if I'm someplace in between 8.5 and 2.0, I have a negative charge on my silica surface and a positive charge on my alumina surface. Good? Now, I told you that PAA is an anionic polyelectrolyte. That means I have this charge, this polymer with all these negative charges on it. So if I'm at a pH at which the surface is negative, I have no affinity of that polymer for the surface of that particle. But if I'm at a pH where the surface is positive, then my polymer will strongly adsorb to the surface of the particle. That's what this is. This might be pH of, say, 6. Okay? And that pH of 6, I'm here, right? Here is 6. My alumina particle is strongly positively charged, or reasonably positively charged. Now I get very, very strong adherence of that polymer on the surface. Okay? Interestingly enough, if I take that alumina coated with PMAA and I dry it out, the PMAA does not come off the surface. It stays on the surface. Put it back in water, the material is now self-dispersing. Okay? So I end up with that polymer coating the surface. Well, this is pertinent for us with regard to kaolinite. Okay? Because kaolinite has two surfaces. This surface looks like alumina. This surface looks like silica. Now you can argue that this is aluminum hydroxide based on the bottom. It doesn't make any difference. I mean, I have a hydrated surface here, quite possibly. Okay, so this surface in water is positive charge. This surface in water is negative charge over the pH range of 2 to 8. Reasonable? Okay, my silica surface will be then negatively charged on that particle. So the consequence is if I look at the particle like this, one surface looks like silica, the other surface looks like alumina, and the edges would be some mixture of those two. So if I do the math here, what happens is that I only need enough polymer to coat the aluminum oxide, aluminum hydroxide side of that particle. Any polymer that comes into the surface of silica does not coat the surface. So the consequence is that I bring in a little bit of polymer, and now the whole particle becomes negatively charged, potentially strongly negatively charged. And if you look at this difference here, here I see I'm someplace around 0.2, here I'm around 0.35, as mentioned, okay? And that difference between 0.35 for alumina and 0.2 for clay, kaolinite, is about 58% of my surface is then coated in the case of kaolinite. Okay? And that 58% corresponds to one basal plane surface and the edges. Okay? Now, what does that mean? That means that my dispersant behavior mimics or tells me that the mineralogy of that particle in suspension makes sense. I have one surface looks like silica, one surface looks like alumina. So the only thing that's left is, do I actually end up with that amount of material? And it turns out that if this is 10 to 1, this is L. L is approximately 10. H, the thickness here, is approximately 1. Okay, at 10 to 1, I get that 58%. So that is what is listed here. Okay. By the way, that's why we see a difference in the amount of dispersant demand for kaolinite and for alumina, and also the difference in viscosity we attribute pardon me, a difference in morphology. Surface areas are different, but the shape is different. The average mean particle size is the same. They're both approximately 0.5 micron mean particle size, which is a composite value. Okay, if I go back to here, so we did a simple analysis and say, what do clays look like, basically. We have the, this is the prevailing perspective. I'm going to go back to here. I have a small issue, right? Colloidal nature of kaolinite. All right. 1-to-1 sheet silicate. Okay. And it's important, been there for a long time, blah, blah, blah. We get all that. This guy Van Olfen, actually Van Olfen didn't do it. It was a guy named Tyson, 1942, wanted to figure out the charge on kaolinite particles, and he brought in gold colloids. And gold colloids basically are negative. And so he did not, we pulled this article out of the library, found it, read the article. Actually, I didn't read the article. I had one of my students who spoke German read the article. And we looked for one really critical piece of information. And that is, what pH was this experiment performed at? Right? Because that pH dictates what that charge would be on the surface. And it is not present in his paper. At the time, 1942, colloidal behavior was just getting started in terms of its understanding. Okay? And so when he put these particles in, and then this is a TEM image, and basically these are the gold particles, and they are showing up on the edges of kaolinite particles. But they also show up on the basal plane surfaces. Van Olfen went in later, and he interpreted these results to say, well, the edges of the kaolinite particle must be negatively charged. And that's the prevailing idea. And that is incorrect. There are two surfaces that are negatively charged. Or else you would see a significantly reduced level of dispersion necessary. He argued that the basal planes were similarly charged, edges are opposite, sodium as a dispersant. We're getting back in that problem. Not consistent with mineralogy. So there's the mineralogy, blah, blah, blah. Here's the cartoon version of this particle. One surface would look like silica, one would look like alumina, and then the edges, well, that's sort of a toss-up here. We could argue that they are neutral under normal pH conditions, equivalently charged. And then what? Well, what is my aspect ratio? So we measured several hundred clay particles from SEM images and came up with this roughly 10-to-1. There are some, there's a standard deviation for those values, but 10-to-1. Then you can calculate for a hexagonal platelet what the amount of basal plane area would be, right? Which is the edge times 2 basal planes. This is the relationship you get. And then for only the edge, okay, if I'm taking up 50%, then my thickness has to be 86% of my width. In other words, I need a particle that looks differently. Looks like this. I need a particle that looks like that to justify only absorbing polymer on the surface, on the edges. Does that make sense? Okay. We have a particle that looks like that. So when we do the math here, okay, and you calculate the edge area versus the total surface area, to get 50% in your aspect ratio, you need to be up in this range here. Does this make sense to everybody? So we're calculating what it needs to look like. And then what we find here is one basal plane surface area. This is what we get. Okay, and that 10-to-1 aspect ratio gives me roughly 40%. So these are my measured values for the shape of kaolinite particles. Thicknesses were 103 nanometers, so 0.1 microns plus or minus 30. Width is 1.1 plus or minus about a half a micron. Aspect ratio is 0.095 or roughly exactly 10-to-1. So the fraction of basal plane surface is then 41%. That means I have 41% for the basal plane surface, 41 for basal plane A, if you will, and 41 for basal plane B. Or let's make that S for silica. This equals 82. My balance is 18%. My edge area is 18% of that particle. If I take 41 plus 18, I get 59, and I estimate 58. Make sense? So if I look at that, the shape of that particle, and I look at the amount of basal plane surface versus edge, works out almost perfect that the amount of dispersant necessary is one basal plane and the edge is for all the particles. Good? Independent, if you will, argument for the mineralogy and the nature of these particles in suspension. Okay. So, lastly, this is adsorption behavior. Silica, no adsorption to speak of. Alumina at this pH of 9, there's my alumina adsorption. And then here's where kaolinite falls in, actually adsorption measurements. Okay. And it works out to be just about exactly 58, 59%. And then here's at pH 6. It's a little bit different, but still similar. And where we are is pretty close to being the ratio for these materials. I'm going to end here. See you on Wednesday. If you wish to take the exam on Friday, I will come up with a time for you to do so. And then it will be given next Wednesday, a week from this coming Wednesday, which I believe is the 2nd of October. Good? And I will post the spreadsheet on Canvas for you for homework 1. Good? Well, if my assistant is in today, we will do it today. So yes, it's not quite correct. I will not post anything. Have a good day. Happy solstice. Or actually, equinox.